Yeah.
Okay, welcome everyone. So it's my very pleasure to introduce Sara Ellison today. So Sara got a PhD at the University of Cambridge in UK, working with Master Pini. Then she won the Legal Fellowship and she moved to Chile. And it's impressive that just 1 year later, she got her fellowship with the Canada Research Chair Year 2. That is a national-wide program for emerging researchers. And she is a full professor since 2015 at the University of Victoria in Canada. And she has wide collaborations all over the world, and she won many prizes and awards. And in the years 2020 and 2021, she was also the president of the Canadian Astronomical Society. And apart of the science, she has also many hobbies, including she is very strong in triathlon, if you want to challenge her. And she just published also a book. It's a guide for people that like to go snorkeling in the beautiful British Columbia. So if you're interested in you can talk with her also about these topics. And in science, she is well known for studies regarding interstellar medium, interpretation of absorption lines quasars, galaxy mergers, and star formation and revelation, and so on. And apart of science, she is also a very thoughtful mentor, both with the young students, but also with younger researchers, as I was when I was at UVK working with her. And so today she is talking about the star forming scaling relations using the ALMA-QUEST strategy. So Sara, thank you.
Thank you so much. I'm really delighted to be back in Italy. It's been too long since I was here. This is my first time in Bologna, though. And I really want to say thanks to Salvatore. He's been a very generous host, although he is trying to kill me with food. I think I couldn't stay here for an extended trip, otherwise my triathlon could. So yes, today I'm going to be talking to you about this ALMA-QUEsT survey, so that ALMA-MaNGA Quenching and STar Formation survey. The goal of this survey has been to understand what regulates star formation in nearby galaxies, and in particular looking at star formation on what old scale, so approximately kiloparsec scales. So this is a survey that I've been leading with my co-PI, Lin, who's based at AJA in Taipei. We have a relatively large team, but I just want to highlight two of our junior researchers who have done a lot of the heavy lifting with the data processing and the data analysis. So Xian Pan, who is recently a new faculty member at Tampere University in Taiwan, and also Mary Thorpe, who did her PhD at Vic and is soon to be moving to Frank McGill's group in Bonn. So in any talk about galaxy evolution, I always like to pause to reflect that our appreciation of this very rich population of galaxies that we now take for granted is really only a century old. So 100 years ago, we were still debating whether the Milky Way was its own entire island universe, or whether these smudgy nebulae could be external to our own galaxy. So, of course, one of the people who is credited with opening our eyes to that universe of galaxies was Edwin Hubble. So this very famous diagram that I'm sure you've all seen hundreds of times. This is the classification scheme that Hubble developed a century ago, where he showed that galaxies broadly organize themselves into two populations. So on the left of the tuning fork, you have the population of elliptical galaxies. So these are characterized by spheroidal morphologies, red colors, low star formation rates, and low gas content. And then on the right, the population of disk-dominated galaxies. So spiral morphologies, young stellar populations, and rich in gas. So this was the view 100 years ago, but of course, modern surveys have put this idea of galaxy bimodality onto a very firm statistical footing. So this is a plot taken from an older paper. Many surveys have shown this bimodality in different ways. This is a figure from the cylindrical sky. This plot, what we're looking at is the color distribution of hundreds of thousands of galaxies as a function of the stellar mass. And so the y-axis here is the color, so red are galaxies at the top and blue galaxies at the bottom. So you can see here that again, the distribution organizes itself into two broad classes. And the nomenclature that emerged when we started plotting galaxies in this way was based on color, because we were plotting one of the axes in color. And so the red sequence and the blue cloud. And then it was very quickly noticed that there was this deficit of galaxies with intermediate colors. And so this was termed the green valley. And this is really just a manifestation of that same tuning fork diagram, because the spiral galaxies are the ones that tend to be in the blue cloud, and the elliptical galaxies are the ones that tend to be up in the red sequence. But this distribution in color space is an observable quantity, but it's not really a physical. So we can recast this diagram in something that is more physical. So we change the color axis to the star formation rate, still stellar mass, but now I'm measuring at how many stars that galaxy is forming in time units. So we again see this bimodality, so two populations. But now, because we're plotting this in terms of star formation rate, the nomenclature changed. And so now, rather than referring to the red sequence and blue cloud, it became more common to talk about this in terms of the star formation properties. So this population up here was started being referred to as the star forming main sequence, and down here the passive sequence, or the quiescent or the quenched sequence. Those terms all basically mean the same thing. So one of the ways that we can characterize this distribution now is by how unusual the star formation rate is for a given galaxy. So I'm going to just spend a moment talking about this metric that I'm calling delta SFR, because I'm going to be using this metric a lot through the talk. So we can draw a line through the star forming main sequence, so where most of the star forming galaxies are located. And then we can just compute a vertical offset. So at fixed stellar mass, does the galaxy have more or less star formation than the majority of the star forming population? That's all this delta SFR is. Now it's in log space. So if the delta SFR is +1, it means that galaxy is forming stars at a rate of 10 times what we would expect for the average. Likewise, if it's -1, its star formation rate is a factor of 10 below what we expect for the average. So now you can imagine taking a vertical slice at any given mass here, and you'd end up with this bimodal distribution of delta SFR. And by definition, the majority of the star forming galaxies will have a delta SFR of 0. So this cyan line corresponds to this cyan. And so now we have these star forming galaxies here, the equivalent of the green valley, where there aren't many galaxies at intermediate star formation rates, and then the quenched sequence that corresponds to these galaxies down here. So one of the burning questions in galaxy evolution for years has been, why do galaxies transition between these two sequences? What causes a galaxy that was happily forming stars to quench, to stop forming those stars? Now, we might naively think that this is just sort of a passive evolution where the galaxy starts off with lots of gas, eventually it uses up that fuel, and so it transitions down onto the quenched sequence. But we have good reason to believe that it's a lot more complicated than that. Just to show you one piece of evidence, this is taken from a simulation, fairly high resolution, with state-of-the-art interstellar medium physics included. So this is the same set of axes, stellar mass, star formation rate. These solid lines with the shaded region, these are observed values of the star forming main sequence, albeit at slightly higher redshift slope. And then these colored squiggly lines, these show the evolution of individual simulated galaxies. And so the galaxies build up in stellar mass. but they don't do so with smooth tracks in star formation. They, through their lives, they're jumping up and down. Sometimes they're on the main sequence, sometimes they temporarily quench, then they go back up. Sometimes there's a starburst that takes them above the main sequence. So there are these multiple transitions around the main sequence. So what might be some of the processes that regulate these transitions around the main sequence and the passive population? So I've already mentioned this maybe naive expectation that it's just gas exhaustion. After a certain amount of time, all of the fuel and star formation is used up, and so the galaxy has no choice but to quench. But an alternative could be that the gas is not used up passively, it is forcibly removed. So one way that you can do this is if the galaxy is in a rich environment, like a cluster, and ram pressure stripping, so as the galaxy is moving through the intracluster medium, the gas gets stripped. An alternative way of removing gas might not be through an external environmental process, but rather something internal to the galaxy. So outflows from AGN are a popular way to do this. So when you have powerful feedback from accretion onto the central supermassive black hole, you trigger an active galactic nucleus, or AGN, and then this fuels winds that can evacuate the gas. Or maybe the gas stays in the galaxy, it's just no longer very good at forming stars. So again, one scenario that has been proposed is something called morphological quenching. So you still have gas in the galaxy, but the presence of a massive bulge stabilizes the gas in the disk, so it is no longer able to fragment and form stars. Now let's think about mechanisms that might take a galaxy above the main sequence into this so-called starburst regime. A very long-standing and popular mechanism to achieve this is through a major merger, so the interaction of two approximately equal mass galaxies. But we have good reason to believe, both from simulations and observations, that minor mergers, where you have a companion that's much lower mass, can also trigger star formation. But there are many secular processes that also might produce a starburst. So one possible scenario is with a bar. So bars are formed in mergers. It's actually the mechanism for generating the central starburst. You have this non-axisymmetric structure, funnels gas towards the center. So you could have secular bars that could do the same job. Another way is if you have a very gas-rich disk. This is probably more likely ongoing at high redshift than low redshift. This very, very gas-rich disk is very unstable, fragments, and you get clumpy star formation throughout the disk. Alternatively, it could just be that you have an environment that is flooding the galaxy with gas along these cosmic filaments. And then, just as AGN have been implicated as possible mechanisms for quenching, they've also been suggested as a possible way of triggering a starburst, because if you have these outflows in the skin of that wind, you pile up gas, and maybe that can also bump up the star formation rate. So we have this smorgasbord of possibilities. How are we going to distinguish which is actually operating in the real universe? Well, our friend in trying to disentangle these possibilities is looking at the spatial distribution of star formation, because we would expect a very different signature if the starburst is happening in the bar region. So we have enhanced star formation in the bar and the nucleus, as opposed to seeing clumpy star formation in the disk, as opposed to seeing star formation in the outer regions of the wind. So an example of how we can do this is by using integral field unit, or IFU spectroscopy. And there are a few instruments around that do this in some large surveys. I'm going to be focusing on the MaNGA survey, which is one of the Sloan components. So MaNGA is now completed, 10,000 galaxies, all public. The way that MaNGA works is it takes the individual Sloan fibers, it bundles them together into these hexagonal units, and then you place the whole bundle over the face of the galaxy. So you don't just get a single spectrum from the center, you also get a spectrum from each of the individual fibers, and then they dither the IFU around to fill in the gaps around. And so by placing these bundles, which have different sizes, so you can match them to the different sizes of galaxies, you then get these hexabundle maps of all of your favorite spectral properties. So some that you derive directly from the spectra. So for example, the velocities in the gas, the velocities in the stars, but then of course you can fit these individual spectra with your favorite models, and then you can derive things like the stellar mass. You can also then measure the emission line fluxes, like star formation rates, gas phase movements. So to orient you with how we're going to use this spatially resolved information, I'm showing you a figure here taken from a paper that I wrote about 5 years ago, working with one of the earlier data releases from MaNGA. So what I'm showing you here is that the distribution of MaNGA spaxels, where we're measuring the star formation rate density in each of the spaxels as a function of the stellar mass surface density in each of the spaxels. And for the redshift of the typical MaNGA galaxy, which is about 0.03, each spaxel corresponds to about a kilomass. And so the color coding here is just by the density of spaxels. So what you can see is that there is this clear correlation between the surface densities of these two properties. And this has been found long before this work, and had been termed the resolved star forming sequence. It's just like the global star forming sequence that I've already introduced, where we have the total star formation rate and the total mass. This is now the same idea, but for individual kiloparsec regions. So just as we defined this delta SFR for the global values of star formation, we can do the same thing for individual spaxels. So we can ask ourselves, is an individual spaxel more or less star forming than I expect for the average of this sequence? So my apologies that the Greek letters start to get a bit of a mouthful, but this is now the delta sigma SFR, it's the offset of this surface density of star formation rate. So now you can start to measure where in the galaxy the star formation rate is boosted and where it's suppressed, because that's what this delta sigma SFR is capturing. Just so to show you one application of this, in this 2018 paper, what we did was we divided galaxies by their total delta SFR. So we took slices through this global star forming main sequence, and then we looked at the radial profiles of their delta sigma SFR. So to explain maybe by a case study, if you take the galaxies, all of the galaxies that are far above the main sequence, so you take all your starbursting galaxies, and you average all of their spaxels together, so as a function of radius, we can then measure the average delta sigma SFR. What we found was that the star formation rates are enhanced relative to the expectation, i.e. we have a positive delta sigma SFR. So at all radii out to about 1.5 effective radii, there's always this positive value, but the value is most enhanced in the inner regions. And then these other colored lines are for other cuts in terms of delta SFR. And then down at the bottom, these are the galaxies that are closest to quenching. So that's the red line here. And we found this sort of nice mirror image between the starburst galaxies, that the quenched galaxies have suppressed star formation rates throughout their disk, but it's the inner regions that are showing the greatest quenching. And so what we found just from the MaNGA data was that this star formation regulation was preferentially happening in the inner regions. So this is all well and good, but really if you want to understand star formation, you need to know about the gas. And so that was the motivation for the ALMA-QUEsT survey. So what we did was we took 46 galaxies from MaNGA and we observed them in CO1 to 0 with ALMA. And we chose the ALMA configuration so that the spatial resolution was well matched to MaNGA. So as we have spaxels in MaNGA, we could match that to elements in the ALMA data. So just to show you some of the data, so these are 3 of our example galaxies. The magenta line, if you can see it on the screen, so that's the footprint of MaNGA. So we have these hexagonal maps from MaNGA. So this is the strength of the H-alpha emission line, which is what we use to measure the star formation rate. And then here is the CO map from ALMA. So this doesn't have that hexagonal window like MaNGA. This is showing you the distribution of our targets in terms of their global star formation rate stellar mass. And the important thing to know about ALMaQUEsT is that we chose galaxies with a range of delta SFR. So we have some that are on the main sequence, we have some that are down in the Green Valley, and then we have some central starbursts, so that we can really compare the gas and star formation properties in the starbursts, the normal galaxies, and those that were mentioned. So really for the rest of the talk, I'm going to focus on just 3 quantities, 3 surface densities. I've already introduced the surface density of star formation rate and stellar mass that we get from MaNGA. But now from ALMA, we can also measure the surface density of the molecular gas. So you'll see there's some smoke and mirrors here. What we observe is CO, and got the subscript H2 here. Many of you know that there is this conversion factor between these 2 things. I'm happy to talk about that in the questions if you're interested. So these 3 surface densities could be combined pairwise in 3 different ways. And it's these scaling relations between these quantities that I'm going to spend most time on in this talk.
Can I ask you how you derive this density?
Yeah, so this is from MaNGA, so it's a full spectral fit to.
The spectral or?
No, it's just the line spectrum. Yeah, so we don't include photometry from long term. So it's from optical, the fit to the optical spectrum.
It's not the idea for stellar mass.
Well, it's actually not bad. So in not this survey, but in another survey, we compared this to using UV plus infrared photometry, and we actually get rates. So we have found, well, you can be the judge when I show you the results, but the scaling relations that we find, they're very tight. So this is the Kennicutt-Schmidt relation. So this is a very well-known scaling relation between the star formation rate and the molecular gas surface density. So this has been looked at many, many times over the decades, both for global relations and for kiloparsec and even parsec scales. So there's nothing really new here. This is just showing you the ALMaQUEsT view of the Kennicutt-Schmidt relation. I've shown you this one already. So this is the star forming main sequence. So again, nothing really new here. This is showing you just what we find for the MaNGA sample. So the correlation between the star formation rate and stellar mass. And then the third way that you can combine these quantities is to look at the molecular gas and the stellar mass. And this hadn't really been looked at in the past, so we had to invent a new name for it. So we call this the resolved molecular gas main sequence. And so again, you can see this tight correlation with only 0.2 depths of scatter. So given that there is a correlation between each of these pairs of variables, it's probably no surprise to see that we can actually combine these variables in a 3-dimensional space, and we see this sort of cigar or sausage shaped structure. I guess I should say salami shaped structure. So the individual black points, these are the individual spaxels. And then the colored contours here are showing you the projections onto those 2-dimensional. This was first published in this paper by my collaborator, Ning-Hui Lin. And in this paper, she assessed what the sort of root cause was for this 3-dimensional space. I don't have time to go into this in too much detail. I'll just give you the punchline. What she concluded was that the molecular gas main sequence and the Kennicutt-Schmidt relation are the sort of the 2 drivers of this distribution. And so really this star forming main sequence that we've come to talk about so much over the decades is really just a byproduct it falls out because these two relations exist, and it's in no way fundamental. This was the first paper to demonstrate this, and there have actually been several others using different data sets that have come to the same conclusion since ours. So now we're going to unpack these galaxies a little bit more. So the figures I've shown you so far are combining all of the spaxels for all of the galaxies. What I've done here is I've now broken out a subset of the sample. So each panel is an individual galaxy. The grayscale is the same in each panel. That is all of the star-forming spaxels, and that's just there for reference. And then the red points are the individual spaxels for that given galaxy. So what I want you to take away from this plot is two things. First, there is a resolved Schmidt-Pennicutt relation for all of these galaxies. So there's a correlation, a nice tight ordering for all of these galaxies. However, the exact details of that relation, so the normalization and the tilt, is different from one galaxy to the next. So sometimes we see it's above the average, sometimes it's below the average, sometimes it's right on it. And then sometimes we have steeper slopes or flatter slopes. And so there is, in one sense, a Schmidt-Pennicutt relation that exists for everything, but it is not a universal one. This has also been found in some other samples now. I think Viviana has done this very nicely with Dustpedia as well. So we can look at the same thing with the star-forming main sequence. So again, on a galaxy by galaxy basis, yes, there is a star-forming main sequence for all of the galaxies, but once again, we see that it is different in every galaxy, and the same conclusion when we look at the molecular gas main sequence. So we can collapse all of these panels into just 3 plots. So we have a plot for the Schmidt-Pennicutt relation, a plot for the star-forming main sequence, and then one for the molecular gas main sequence. And now each of the red curves is the smoothed sequence for each individual galaxy. And so what we can see is that most of the scatter that we see when we put all of the spaxels together is not due to measurement uncertainty, it's due to real galaxy to galaxy variation. And so then we ask the question, well, why? Why are some galaxies above or below these different relations? So we try to take a look to see whether these offsets correlate with any global variables. We do find some weak correlations. So in particular, the morphology of the galaxy seems to weakly drive this. So for example, how far above or below the star-forming main sequence you are, or how far above or below the Schmidt-Pennicutt relation you are, has these weak anti-correlations with the SERSIT index. Okay, so far, I've only been showing you results for spaxels that are actively star-forming. This is sort of a cut that we do in the data set. But as I mentioned at the beginning, one of the key questions we wanted to address with this work was what was regulating the quenching of star formation. And so in contrast with selecting star-forming spaxels, we can also select regions in the galaxies that are suppressed in their star formation. So they are on their way to quenching. So they're not fully passive yet. So we call them retired. They're kind of they're on their way. The way that we basically select spaxels that are retired or quenching is basically based on their low H alpha equivalent width. So this tells us that the photoionization is no longer dominated by very young stellar populations, but rather than by the older stellar populations. So here we are again with the molecular gas main sequence that I've shown you several times now. So how much gas you have per unit stellar mass. For reference, these blue contours here, those are the star-forming spaxels that I've already introduced. And now in the orange contours, I'm showing you the distribution of spaxels that are retired, that are quenching. So what you can see is that there's still a sequence here in the retired spaxels, but it's offset from the star-forming spaxels. in the sense that at fixed stellar mass, the surface density of molecular gas is lower. So another way to say that is their gas fractions are lower. You can see that explicitly in this inset. So the gas fraction that I'm plotting here is just this divided by this. So we can see the distribution in blue for the star-forming spaxels and in orange for the retired spaxels. So what this shows us is that the gas fractions in the retired spaxels are lower by 5, hinting that part of the reason for this quenching is because they have less gas. They're not fully devoid of gas, but they just have less of it. Just as we've done before, we can unpack this on a galaxy by galaxy basis. So I'm showing you 8 galaxies here. Again, this is the molecular gas main sequence in each panel. The grayscale, again, is showing all of the star-forming spaxels in the full sample as a visual reference. The blue are the star-forming spaxels in that galaxy, and the orange are the retired spaxels. And so again, you can see that there is clearly a distinction in terms of the molecular gas properties of these regions that are quenching. And so again, we can plot that in terms of the gas fractions to see explicitly the difference in these distributions. So typically the offset is a factor of a few, but in some cases it can be as much as 100. So as I sort of advertised at the beginning, we can get information about the processes of boosting the star formation and quenching the star formation by looking at the spatial distribution of these properties. So here are 4 example galaxies taken from ALMA-QUEsT. And again, the purple hexagon just shows you the MaNGA footprint where we have data. And then in the panels below, I'm color coding the spaxels by whether that particular region is star forming, in which case it's blue, or if it is retired, in which case it is orange. And if it's gray, it means it doesn't fulfill the criteria for either of those. So it's in the kind of other category. So what you can see is that in all of these cases, the retired regions are more central than the star-forming regions. In some cases, they're truly central. In other cases, they are more central, but they're in maybe a sort of a ring. And then these empty regions in the middle, sometimes that's because there is photoionization that's more like a liner, or it's fully quenched and there's no emission. But the general properties that we see, the general trends that we see is such that the retired regions are preferentially in the center. This tied very closely back to the MaNGA results that I showed you at the very beginning, where we were seeing that the star formation is preferentially quenched in the center. So one of the very popular interpretations for this inside-out quenching has been that it is driven by an active galaxy. So you have a big power source in the middle of the galaxy, and it's shutting down first the star formation in the middle, because that's where it's doing the damage first of all. So we'd like to be able to test this. The problem for us was that ALMA-QUEsT doesn't have many AGN in it. It has maybe 1 in it, so it was not a good sample for us to make that test. So instead, we had to use a different sample. But again, we needed to be able to measure the gas, because if you want for the AGN to shut down your star formation, it had better be doing something to the gas. There has been this big debate in the literature, though, about whether AGN can really be responsible, because low redshift AGN host galaxies seem to have totally normal gas contents. So there have been many, many papers on this. I've shown you just a few examples, here in my literature list here. 2 figures to demonstrate that. First of all, measuring the atomic gas, and then measuring the molecular gas. So in this paper, what we did was we measured how much H1 there was in an AGN, so a BPT selected sample of low redshift AGN in Sloan, and we compared that H1 gas fraction, where the H1 was coming from stacks of alpha data. We also did it with deeper X-gas observations as well, and compared it to a sample of non-AGN hosts. And so what you can see is that the AGN and the non-AGN have very consistent neutral gas fractions, atomic gas fractions, possibly with the exception at the lowest stellar masses, but for most of the population, very consistent. We can do the same thing in the molecular gas. So this was a paper led by Mike Pos. So now we're looking at the molecular gas fraction as a function of the specific star formation rate. Again, comparing AGN host galaxies, this time these are X-ray selected from the back survey, compared with normal star forming galaxies. And so again, we see that these two populations lie on top of one another. So a wealth of literature arguing against AGN feedback because the gas fractions were consistent. But our kind of question was, well, maybe the AGN doesn't affect promptly the global gas. Maybe when you see the AGN on, it's only just starting to get its claws in, and so we need to look in the resolved properties. But as I said, we didn't have many AGN in the ALMaQUEST survey, so instead we used a different data set, somewhat similar in its design and construction to ALMaQUEST, in the sense that it builds on an IFU survey, in this case CALIPHA, combined with matched resolution in CO, in this case EDGE. So the EDGE CALIPHA survey, as I say, similar in spirit to ALMaQUEST. It's a larger sample, it's about 120 galaxies. It's mass selected. It's complementary to ALMaQUEST, but ALMaQUEST has the leverage in terms of star formation rate. This survey has the leverage in terms of numbers. So we identified 4 AGN, so again, BPT selected AGN in the EDGE CALIPHA sample. And in particular, what we wanted to make sure is that each of these AGN that we identified had these sort of star-forming disks, that AGN-dominated centers. So we played the same game with EDGE CALIPHA that we have with ALMaQUEST. We make this molecular gas main sequence. So now all of the data you see here are EDGE CALIPHA. So the blue is the star-forming spaxel sample from EDGE CALIPHA. So you can see, just as in ALMaQUEST, there is this nice sequence. The orange contours are the retired spaxels in EDGE CALIPHA. So just as we found in ALMaQUEST, there is a sequence here, but it's offset in terms of gas fraction. So here's the gas fraction inset here. So you can see the orange histogram is shifted to lower values compared to the blue. And then the individual red points are the AGN spaxels in the EDGE CALIPHA. So these nuclear VPT dominated AGN spaxels. And so what we found was that just as the retired spaxels are offset to low gas fractions, the same is true for the AGN. And so just as we've done before, we can split this out galaxy to galaxy. And so we see that in each individual galaxy, there are these lower gas fractions, so the sequences are clearly offset from the star-forming spaxels in those individual galaxies, which again corresponds to low gas fractions. Okay, so maybe AGN plausibly have some effect, but in order to see it, you have to look on these resolved scales. So it's not affecting the gas in the galaxy as a whole, at least not when you see the AGN on for the moment. But on these smaller scales, there is some effect. Okay, so hopefully what I've shown you with both the retired population and the AGN population is that the gas fractions seem to be low. But this might not be all of the story. So there are broadly two ways that you could think about lower star formation rates. So one way is that you reduce how much gas you have, and so you can't make as many stars. But an alternative way is you make the gas that's there less efficient at forming stars. That can happen for a number of reasons. So, for example, this morphological quenching I talked about. So there's gas that's still there, it just doesn't fragment. Or if you have a merger, it's really turbulent, same AGN wind, but it heats up the gas. So we really need to look at both of these effects. The way we're going to do this is again using offsets from these scaling relations, which hopefully you're a little bit oriented for now. But in any case, I have this cartoon view of how we're going to use offsets from these scaling relations to assess the relative contribution of gas fractions and star formation efficiencies. So let's imagine we have a region in a galaxy where the star formation rate is low. So it has a delta SFR less than 0, telling us that that spaxel is located below the star formation sequence. And our question is, did it get there because of low gas or low efficiency? So if it gets there because of low gas fraction, that spaxel should be offset from the molecular gas sequence. Right? This is what this is measuring. It's saying for my stellar mass, I have less gas. And we've seen that that is at least part of the answer. I've shown you that already. But maybe there is also a star formation efficiency piece. So if it's just gas, we would find that spaxel offset in this scaling relation. But that lower gas would just slide it down the Kennicutt-Schmidt relation, and its star formation efficiency could still be totally. The alternative view is if this low star formation rate is because of a normal amount of gas, so the spaxel lies on the star formation sequence, but that parcel of gas is not very good at converting itself into stars, and so it is offset from the Kennicutt-Schmidt. So all of these delta properties, so we've seen delta SFR a number of times now, but we also have a delta gas fraction and a delta star formation efficiency. Looking at these offsets can give us a clue. So to show you how we can investigate this, I've got sort of two experiments. One is a sort of old-fashioned one, if you will, where we can just look at the correlation between the star formation rate changes and then either the gas fractions or the star formation rates. So this particular paper was using this special sample of 12 particularly starbursting galaxies in ALMA-MaQUEsT. And so we're looking at the offset in the star formation efficiency in this panel and the offset in the gas fractions. So what we found was that the trend between the star formation rate changes was stronger with star formation efficiency than with gas fraction. There's a weak correlation as well with the gas fraction, but it's more the efficiency, and in particular, the really starbursting part. So this delta SFR +1 means 10 times the star formation rate. All of these spaxels had significantly enhanced star formation efficiencies. But we can also do this with a more sophisticated analysis. And for this, we moved beyond just looking at the starburst sample, and we took the whole of the ALMaQuest sample together, so it's about 12,000 individual spaxels. And what we did here was we approached this with an artificial neural network. So essentially the way this works is you have many, many variables, and you ask the artificial neural network, the ANN, which of these many, many variables is the best predictor of a certain target. So in this case, we gave it the target variable was the surface density of the star formation rate. And this IOR, this means the improvement over random. So this is just how important these different variables are. We tried this with tens of different variables. I'm just showing you a handful here. So just to remind you, the star formation efficiency is the star formation rate per unit gas, so how good the galaxy or the region is at converting the gas into stars, and then our gas fraction is the gas per unit stellar mass. Okay, so when we ran this experiment for these 12,000 star forming spaxels, we found that if what you want to know is the star formation rate, the most important thing that's going to predict it is the molecular mass. Now, this is not particularly profound. This is just the Schmidt-Kennet correlation. What we actually wanted to know was not how do we predict the star formation rate. We want to know how you predict whether it's above or below the main sequence. So it's the target that we really care about is this delta sequence. So now the raw amount of gas turns out to be relatively unimportant. It's actually the change in the star formation efficiency, and to a lesser extent, the change in the gas fraction that played the biggest role. So whilst gas fraction does play some role, actually the star formation efficiency seems to be the greatest. I've only had time to talk about a relatively small number of results from the ALMaQUEsT survey. I just put this slide up here now in case there are other things that you're particularly interested in. If you care about galaxy mergers, if you care about rotation curves or some dynamical things, there is plenty to choose from on this this menu of ALMaQUEsT papers, and more to come. Okay, so I'll leave you with my summary. I've introduced the ALMaQUEsT survey, which is combining MaNGA with ALMA. We have shown that there are these three scaling relations that together form this three-dimensional space, and I've argued that the star forming sequence is really not a fundamental sequence, even though we've been living with it for decades. I've shown you that even though these scaling relations exist in all galaxies, every galaxy is its own snowflake, different. I've shown you that the quenching of star formation is linked to low gas fractions, possibly originating from AGN, although I will grant you our sample of 4 needs to be enlarged. But the gas fraction is probably not the whole story and may not even be the dominant component. Maybe star formation efficiency is even playing a more important role. Thank you very much.